This is my favorite question in the paper. We're going to be deriving a result for this summation, but to do so, we're actually going to use this idea and sum up two summations. Now, at the heart of this, we're going to have Euler's relation. E to the I theta is cos theta plus I sine theta. We'll be bringing that in a minute. But first up, let's work out then C plus IS. Well, it's going to be just this added to this, but just with an I in there. What I'm going to be doing is adding like the pairs. So cos theta plus I sine theta. And then it'll be plus a half. And I could even factorize out the half cos 5 theta, 5 there, plus I sine 5 theta, plus a quarter cos 9 theta plus I sine 9 theta, and so on. But then using Euler's relation, I'm going to get e to the I theta plus a half e to the 5I theta plus a quarter e to the 9I theta, and so on. And if we look at this, we can see that each time we're timesing by a half e to the 4I theta. We've got ourselves a geometric series. So the common ratio is a half e to the 4I theta. The first term is e to the I theta. Therefore, C plus IS, we can now use the sum to infinity formula. This isn't the formula book, of course, but it's so simple I'd learn it if I was you. We're going to get e to the I theta over 1 minus a half e to the 4I theta. And we're nearly there, just times top and bottom by 2. 2e to the I theta over 2 minus e to the 4I theta. Let's show that this is true. So what we're going to be doing is looking at the imaginary part of the left-hand side and therefore the imaginary part of the right-hand side. But before I do that, we need to just make this a little bit neater. And what we can do is basically deal with the division. So if you ever have 1 over 1 minus I and you want to work out that division, you can times by the complex conjugate 1 plus I over 1 plus I. Because you get 1 plus I over 1 plus 1 over 2. Now, then you got your complex conjugate, and if you wanted the imaginary part, you can see it's just going to be a half, which you can't really see from here. So we're going to be using that same idea. And the complex conjugate just means you replace I by minus I. So we're going to be timesing, well, we've got 2 minus e to the 4I theta, and we're going to be timesing by 2, still a minus here. See, that's what makes this one a little bit different. Here we changed it to a plus, but the I is actually in the exponent. So it's going to be 2 minus e to the minus 4I theta. That will necessarily sort it out. We know that the complex number times its conjugate will give us a real number. That's the whole purpose here. I'm also going to go through this a second way in a minute, where I replace by sine and cos earlier on and then do the complex conjugate. I think this way is slightly quicker, less likely to lead to mistakes. So on the top, we're going to get 4e to the I theta minus 2e to the minus 3I theta. Then on the bottom, we've got 4 minus 2e to the minus 4I theta minus 2e to the 4I theta. So in this case, they don't cancel like they do for this one here. And then it's going to be plus 1, in fact. All right, time to use Euler's relation, I think, again. So we're going to get 4. Remember, we're going to be looking in the imaginary part in a minute. So 4 cos theta plus 4i sine theta minus 2 cos minus 3 theta, but that just is the same thing as cos 3 theta. And then I'm going to get minus 2 I sine to the minus 3 theta, but that becomes plus sine 3 theta all over 5 minus 2 cos minus 4 theta. Again, that's just cos 4 theta. Then it'll be minus 2 I sine minus 4 theta, which again just becomes then a plus. I'm just cancelling it out as I go along, making it, sorting out the negatives. Then minus another 2 cos 4 theta, and then minus 2i sine 4 theta. Remember, we knew that the imaginary parts were going to cancel, so that is comforting. Okay, and then, well, actually, we're pretty much there. The only thing is, okay, I'll separate it into real and imaginary parts. We're going to get 4 cos theta minus 2 cos 3 theta over 5 minus 4 cos 4 theta plus 4 sine theta plus 2 sine 3 theta over 5 minus 4 cos 4 theta, just a factorized out an I. And then what we can do is we can equate the imaginary parts, and we're there. So what a great result. S, this infinite summation involving trig functions, is equal to 4 sine theta plus 2 sine 3 theta all over 5 minus 4 cos 4 theta. All right, I'm just going to go through this in one other way, and it's to go back to the original formula, but instead of timesing straight away by the complex conjugate, getting it in terms of sine and cos. Do you know what? I I don't know. I don't think there's much in it, to be fair. So we've got C plus IS equal to this, and then that's going to be 2 cos theta plus 2I sine theta all over 2 minus cos 4 theta minus I sine 4 theta. And then I'm going to times by the complex conjugate, more kind of like traditional form this time, instead of just, but I'm still just changing my I to a minus I. So I'm going to times by 2 minus cos 4 theta plus I sine 4 theta. We've just got to really carefully deal with the brackets now. So we will get 4 cos theta minus 2. Do you know what? This is more involved, I just remembered. Because we end up getting things like this, cos theta times sine 4 theta, and we have to bring it together in a minute. Okay, still got loads more to do. Then I'm going to get plus 4 I sine theta minus 2i sine theta cos 4 theta. Then 2i times I gives me minus 2, so I'm going to get minus 2 sine theta sine 4 theta all over. Now what we can do is just kind of bring this all together to start with. So 2 minus cos 4 theta squared. And then when you times it, it's a bit like that 1 plus I that I dealt with before. When we times by I sine 4 theta and then by minus I sine 4 theta, those imaginary parts are going to cancel. And we'll just be left with plus sine squared 4 theta. So I think I'm going to go straight into now equating the imaginary parts just because of how complex this is. No pun intended. And for S is going to equal 2 cos theta sine 4 theta plus 4 sine theta minus 2 sine theta cos 4 theta. Just taking the imaginary parts in the numerator. Let's expand this bracket now. I'm going to get 4 minus 4 cos 4 theta plus cos squared theta 4 theta, sorry, plus sine squared 4 theta. But hey, this is just equal to 1. And then sine 3 theta, if you use your um, addition formula, is sine 4 theta minus theta, which is sine 4 theta cos theta minus sine theta cos 4 theta, which is precisely what we've got here, just multiplied through by 2. So we're going to get, actually, let's write it in the way they had it. We're going to get 4 sine theta plus 2 sine 3 theta. All right, I take it back. Don't do it this way. This is actually how I did it. I don't know why. I just got it in terms of trig functions. It still works out. It's just I think the examiner's report talks about like people going this route and more likely to make mistakes. You know, there's a lot more multiplying brackets out. You've got to notice that addition formula result, but we get there. But yeah, this is really the way to do it. Work in terms of exponentials. Just remember what to times through by the complex conjugate, and then it will work out really nicely. So yeah, amazing result. This summation here is simply written like this, and we could write the one down for cos as well because we just by equating the real parts. Amazing.